Okay, so now we'll be doing in some quick examples, and this time what I'll be doing is primarily we'll be defining in relations. Now, in a C program, if you want to define a function, you go int sum, int a, comma, int b, return a plus b. Logical programming is all declarative. Everything is declared as statements. So if you want to define relations, that's how you do it. And while defining sometimes some relations, you accidentally happen to infer, derive new properties, new theorems, and those get added into the knowledge base as well. So even though it may look immensely primitive, let's define something. So, examples of relations, let's define the relation mother. It's a function actually, everybody has one mother. So, let's define the function mother c is equal to m. So it's defined and it's actually a bijection, like all definition, it's implies and it's implied by. So a mother is nothing but a definition that you get from another relation, which is a parent. So if M is the mother of C, M is of course the parent, and you've got the fact that the female component of the parent is called as a mother. So that's what holds good for all child C and mother M. Mother of child C is the mother M. Father would be absolutely similar. Let's just skip it up. So let's define husband and wife. Husband H to the wife W. So this gets implied and it's implies by, I can also say H is equal to husband of W. It's defined by another relation which is called as a spouse. And of course, the male part of the spouse is what is a husband, and similarly for the wife. This needs to hold good for all H and W objects. This time I'm not underlining it up, it's obvious. I've used a small case. So let's define in. Okay, now I need to define in parent, of course. So P is the parent of a child C if so P is the parent of the child C if C is the child of the parent P. They are pretty much inverse of each other. The orders actually change. In fact, I may have written this up. M is the mother of child C. As long as you consistently get the ordering correct, it's absolutely okay. This needs to be hold good for all parent P and child C. Let's define an interesting one, the grandparent of the child C. So the grandparent will of course be defined in terms of parents. So G is a grandparent of C if and only if you have a P as a parent of C and G as a parent of P, of course. So P is a parent of C and G is the parent of P, and there needs to be at least one such parent P. So this is also what is there exists and for all in a nested structure. As long as I get one such P, this relation satisfies. Of course, you will get in exactly one such object P. Let's define in lastly siblings X and siblings S1 and S2 for all S1 and S2. So that's an interesting relationship. S1 and S2 are sibling if they have a common parent. So P is the parent of P S1, and P is also the parent of S2. If they have a common parent P, there exists one such P, then S1 and S2 are siblings. And again, as in the last example, I need to specifically add that S1 is not equal to S2, otherwise S1 and S2 could point out to exactly the same object, and if they point out to exactly the same object, then it doesn't hold good. So very quickly, moving on to some other definition. This time, let's take the definitions from sets and let's define a few functions out over there. Now I'll go more practical because kinship, which is mother, father, parent, child, the definitions were not recursive. Now we'll have our standard bigger problem defined in terms of smaller, smaller still, and smaller, and all those which are used to define a thing. So let's define something which is called as set S, and of course, in order to define a set of something S, what I'll do is that I will define it in terms of a smaller set S2. So this complete thing is what is a S. It comprises of a S2, and then let us just extract out one item from it, which is a S. So a set can be defined in terms of a smaller unit, which is a set S2. And what you really go upon doing is that you say the relation X added to the set S2 gives you a bigger set. So S is given by what I get when I take S2, I add S2 over it. This is a standard list operation, which is X added to the set S2. So if I get any such X and S2, I get any one smaller problem like this, then my bigger problem is what is defined. Now, in every recursion, there has to be a base condition, like it or not, for all S. So, the base condition is what's the smallest set that you can think of? This one. So, let's just add it around over here. So, S is either blank, this is the base condition, or the non-base condition, a bigger set defined in terms of a smaller set. This one is inquisitive, which is an empty set, of course. How do I define that empty set? So let's do it very quickly. So empty set is something on which nothing can be added. So on any general set S, if I add X, I get in a larger set, and my larger set cannot be empty. So let's prove it by contradiction. I say this is equal to empty, and then I'll say that this statement is completely null and void. It's completely invalid. It's completely invalid. That means there exists no solution, or this is not satisfiable, or there exists no such S and X. So there exists no such S and X. I normally write it down like this, but I haven't taught you this, so I will have to put a not sign before it. So we define the empty set in terms of contradiction. We said some X added on S produces this empty set, and then we said this statement is null and void. It's completely unsatisfiable. Unsatisfiable, that means there exists no solution. There does not exist any such X and S. Let's go down to the membership function. X is a member of S. So how do I define X is a member of S? And then again we use the standard bigger into smaller theorem. So for S to be, I define my S as a bigger one. I define S2, which is nothing but one element taken out of it, and then this time because X has already been used, so let's rename it as Y. a bigger defined in terms of a smaller. I need more space. Yeah, so X is a member of S. This can be defined by in terms of these quantities as first let's define the set S. So what did I do? I did exactly the same thing. So I added y on top of S2, and after adding y on top of S2 I get S. So this is my definition of how do I get in my set S. Now I'll go upon to the actual definition. Now membership, X is a member of S, larger problem divided into smaller problems, two smaller problems, a unit 1 and of size 1 and a problem of size n minus 1. In order for X to be in S, it must be either here or here. So let's define it. Either here, X is equal to Y, or here, X is a member of S2. So there's a smaller problem, that's a larger problem. If there exists any one solution like this, Y and S2, and this needs to hold good for all S. So that's how I get in what is my membership. Let's go into, now it'll become absolutely easier. Subset S1 is a subset of S2. And this, I mean, I'll not go by the standard way. I'll go into a definition that you, of course, have studied for a million times. So if X is a member of S1, it has to imply X as a member of S2 in order for it to be a subset. 5 exists in S1, so 5 has to exist in S2. If 5 does not exist in S1, absolutely doesn't matter whether 5 exists in the set S2 or not, and this needs to hold good for all X. This thing needs to be holding in for all X, and of course, this is a rule which is defined for all S1 and S2. Equality is absolutely simple, and the equality is nothing but, okay, did I forget the bijection? Equality is absolutely simple. So if S1 is a subset of S2 and S2 is a subset of S1, then S1 and S2 are of course equal. You've read that so many times in mathematics, nothing to explain. Similarly, let's go very quickly to union. So S1 union S2. So X is a member of union of X1 and X2 if and only if X is a member of S1 or X is a member of S2. So if X is a member of S1, it will be a member of the union. If X is a member of S2, it will be a member of the union. And this is for all X, S1, S2. Intersection, just change it to and. Why am I going that basic? So let's just getting a little bit more comfortable with what are the quantifiers. Now my actual problem is of course a lot more interesting. So let's get back to see what we are doing. The only things added are 3. I've got my quantifiers now. I've got for all there exists which did not occur into zeroth order logic, and I will have to do something about it. And the second thing is that in my zeroth order logic, I have just cared about true, false. Is R1 honest? Is R2 dishonest? Now my questions are, give me all X such that X is dishonest in AI. So I'll just fire a query honest and I expect all X that satisfy this relation as output. So now my query can be a little bit more weird, that Give me references to the object such that this relationship holds. Give me the names of the object such that this relation holds, or define in the references to the object such that those objects qualify this criterion. And this is what is called as a standard binding list. So which all x bind to the objects in my interpretation such that not honest x comma ai is true. And of course in our example it will return either r2 or best friend r1 or anything else. So that's what it will return. And these are my kind of problems that I'm looking for. So I could either ask, is R2 dishonest in AI? Or I could say that give me all X who are dishonest in AI. I could add in more connotation. Give me all X who are dishonest in AI and who are friends with a student I like the most as rule number 5. So out of all the friends of R5, out of all friends of R5, give me the ones who are not honest. So I could fire a query like this. So the answer will be a binding list or a substitution list or a list of all the x's possible or the names of all the x's possible or references of all such x possible. Now I will of course solve it in a generic sense. There's some way by which people may really solve it in a quick and easy manner. What is our problem with this? Why cannot we just solve it in general like the zeroth order AI, for which the things are already being stated? Now it turns out that my number one problems is there could be infinite objects. So best friend of blah blah R1, and the other problem is unlike zeroth order AI, two people could have the reference to the same object R1 and R5. Somebody doesn't have a name, somebody has two names. So for you, it may be common that in this university all whole numbers are unique. For AI, it's not common sense. And therefore, sometimes people make in assumptions which are known as the uniqueness assumptions. Which means this is not possible. Every object in your interpretation has a unique name, and there is absolutely nothing which does not have a unique name. Domain closure, which means there are as many objects as they are names. So basically both of them combined, everything has a unique name, which is what you see with roll numbers. Roll number 1 is a different person, roll number 2 is a different person, RK is a different person. Everything has a name and everybody has a unique name. These are assumptions that you could place in. And the third one is called as a closed world assumption. So the closed world assumption says that everything is either true or false, but isn't that proposition logic? So if I just ask without giving any facts, anything, is R10 not honest? Now, the result honestly is, I don't know. There is no evidence that R10 is honest, and there's no evidence that R10 is dishonest. I don't know. So there are two types of AI. One in which the system could return, I don't know. I have neither ways to prove R10 is honest, nor I have ways to prove that R10 is dishonest, so I don't know. Those are called as open world assumptions. The other one is what's called as the closed world assumption, where you say if I cannot prove Aten is honest, it means Aten is dishonest, like it or not. So the onus is on you, then, to prove yourself as honest, because if you cannot, if there are no evidences that prove you are honest, it's a closed world assumption. I know the truth, or I can derive the truth of each and everything. If I cannot derive the truth, that means it's bound to be assumed that it's false. And sometimes it may be very intimidating that if you cannot prove something true, it's false. It may, of course, sound weird, but you model the problem in such a way that the closed world assumption is absolutely what is satisfied and justifiable. So, as in the world, most of the entities are true. So, unless you see and observe it's true, you say that, or you can derive that up, you assume it to be doing false.